I'll be talking about Schrodinger's cat and the Copenhagen interpretation of quantum physics. First, let's talk about the Copenhagen interpretation of quantum physics. Erwin Schrodinger and Albert Einstein agreed that the Copenhagen interpretation sounded like nonsense, and Niels Bohr and Werner Heisenberg, the founders of it, tended to agree. The Copenhagen interpretation consists of the following parts. The first, the wave equation. The wave phi says that every particle can be described by a wave function that is related to the probability of the particle can be found. Unlike classical physics, where the trajectory of an object, like the parabola of a free-falling object, can be described exactly, quantum mechanics can only talk about the probability of a particle's current position. Start at the same time anyway. One of the things that Shy seems to predict is that an atom can exist at an excited state and a non-excited state at the same time. This phenomenon is known as quantum superposition. It cannot be observed in nature and is only theoretical because at any given random moment, an atom can only be either observed as only either energized or non-energized, but never as both. This can only be observed by passing an electromagnetic wave through the atom. But that too falls apart when other particles surrounding the atom interacts with it. The second part of the Copenhagen interpretation talks about Heisenberg's uncertainty principle. It states that the position and momentum of an object cannot be accurately measured at the same time when shrunk down to a quantum level. When the position of the object can be measured exactly, the probability becomes infinite, thus rendering this useless. The third part of it is the Copenhagen interpretation is wave-particle duality. As it so happens, lambda, the wavelength of a particle, is inversely proportional to m. And we will talk about this later because lambda for an electron, so a particle as small as an electron, is very, very high and measurable. While larger objects, as in classical physics, like cats and baseball bats, are infinitely smaller and completely minute and cannot be measured at all. The lambda of an electron will always be greater than the lambda of the cat that will be coming up when you talk about Schrodinger's cat. And the corresponding principle states that at large scales, quantum mechanics will correspond to classical mechanics, but something that Schrodinger usually disagreed with. Now let's talk about Schrodinger's cat, which has become immensely popular in pop culture, although albeit a little inaccurately. I'm so sorry. Schrodinger started with a thought experiment where he put a cat, a hammer, a Geiger counter, some radioactive substance, and a vial of volatile poison in a closed box. He said that it would require a sequence of events for the cat to turn up dead. The radioactive substance has to hit a level of decay where the Geiger counter sets off a mechanism wherein the hammer falls on the vial of poison, causing the poison to volatilize, killing the cat. However, the box is closed. Before the box is open, we cannot tell if the cat is alive or dead. This puts the cat in a very awkward position. It is both alive and dead to an outside observer. It exists in the intermediary state inside that box. Oh, I know this sounds like rubbish, and that's exactly what Schrodinger thought of classical mechanics. That the cat cannot exist as dead and alive at the same time, or the electrons and photons have been observed to be in different places at the same time, corresponding with each other over large distances. Thus I conclude this video on Schrodinger's cat. I hope you enjoyed it. Thank you.